Hi there. Behind me is a particle system that creates a helix that orbits around another helix. I provided a link for the code in the description below, but if you want to learn how the different pieces of this work and how I made this program, stay tuned. I'm going to walk through that with you step by step. Here's the program that we're going to do today. You can find this completely annotated version in the description below if you just want to skip this video altogether and learn what you can from the way it's been documented, or we can go through this line by line and I can explain to you how all the pieces fit together. We're going to start by making a new sketch in p5.js, and we're going to change the canvas settings. For the z parameter, we have to tell p5.js that we want to use the z dimension in our canvas. So we're going to go from just having an x and y dimension to having a z dimension, or a depth. P5 has no idea what we're talking about, so we need to give it some tools to do that. And we're availed to those with the web graphics library. We can specify that with all caps WebGL. So put that in the z parameter for the create canvas size. And now p5.js knows we have a depth. So everything's kind of changed. Well, not everything's changed, but with that added dimension, we have some ability to use translate with 3 dimensions. We can use vectors with 3 dimensions. So there's some things that we can use that p5.js had reserved for just the x and y. Now we've got that extra z dimension that we can use. Not everything, but some things are like that. So in the global space, let's declare a variable that will hold our helix making object. Simply enough, we can call this helix. Inside setup, we're going to use that helix variable that we declared, and now we're going to assign to it a new instance of this function. So we're going to use the new declaration, and Helixmaker is going to be the name of my function. So we're just going to put that there. Now all the attributes and goodness of the Helixmaker function has been given to just this variable here. The next thing we want to do is set the background to some color. We're going to do this in setup so that when we start our draw, we have a nice clean canvas to begin with. I'm going to set that to 0. Let's give ourselves some room now that we're ready to move to the draw function. After we set our background to 0, we are going to assign a local variable that's going to hold a sine wave return. And we're going to tie that sine wave to where the viewer is looking at the volume. Basically, we're going to take the origin of that volume and move it toward or away from the viewer along some axis. And toward and away from the viewer would be the z-axis. So that's what we're going to do here. Let's call this cam in, and we're going to use the map function. So we're going to interpolate the value, the return from sine, in the parameters for sine. We're going to use frame count as our incrementer, and we'll just take a coefficient, so multiply it times a fraction. The sine wave will return a value from -1 to 1, and we're going to set that equal to some depth that we're going to move into the z or out of. So maybe negative height, that's our distance away from 0. We'll do 75% of our height away from 0 into the depth, and 75% of the height away from 0 out of the depth. Once we have our push in and pull out value, we can translate the origin to that location. So it's either going to be closer to the viewer or further away from the viewer. Now if you wanted to, you could do something like this. We'll just comment that out. So you can put both translates in there and comment out one, so you can easily switch between the kind of views that you need. So for now, just so we can see everything is working right, I'm going to try to remember that we're not camming in or camming out. So when I test this to see is it working, I don't want to be moving in the camera and moving out of the camera. I just want to be stepped back and checking out and making sure everything is moving and positioned where it's supposed to be. Once that's done, then I can check the push in and pull out. So to do that, I'm going to just comment out the line That will do the push in and the pull out, and replace it with the translate that's fixed about half of the distance to the origin. Once we have it translated, once we have our origin kind of anchored down, now we can spin the volume around that origin. So let's do some rotates. So I want to rotate by a fraction of the frame count, and I want to do that pretty uniformly along the X and Y, and then maybe a little slower along the Z. So you're probably looking at these rotates, and if you're not familiar with this, you're wondering, well, how do you know which one's the X, Y, and Z? In p5.js WebGL, we can specify on this function, this method rotate, we can specify at the end of the word a capital X, Y, or Z, and it will tell p5.js, or WebGL rather, how to rotate the volume. So once we've rotated the volume, now we can display the output however it is. The output itself has basically one orientation, and then if we want to see that from different angles, we need to move the global volume and shift our view around that object. So once we've shifted our view around the object, now we're ready to go inside the system itself and start translating to the locations of these individual positions. To do that, we're going to do it inside the method of the function. We're going to call that method update. So we're going to use our variable Helix, which contains our function instance, use the dot syntax, and we're going to call a method in that function, or function in a function, we're going to name update. So in the future, coming up very soon, we're going to do this Helix update function. So that's everything for draw. Now we're ready to do the Helixmaker function. So maintain that consistency between the name that you use to instantiate it and the actual name of the function, or else you're going to run into a problem. Inside that function, we have another function, a method called this.update, that's going to perform the all the math and generate the output. So in order for us to figure out the math, we need to have our starting values, and that's what we're going to do right here. We need an array to hold our X, Y, and Z. We could use a vector here. Some people aren't real familiar with vectors, so I'd rather just use an X, Y, and a Z when working with WebGL, because once you figure out the X, Y, and Z and you have those down on their own, then you can start using the vectors, because it makes more sense how you're rotating things. Alright, so that being said, let's start in our instantiation space here where our first time variables are declared, or we could just put everything in here and use the same variables, starting variables again and again. But we're not going to be able to change anything that way. So what we want to do is to change stuff as we're making it. And to do that, we're going to isolate any of the changes that we make to the system inside its own little function. So let's set up the initial math, and that's this X, Y, and Z. We're going to declare empty arrays for each one of these variables, and it's going to hold a coordinate value. So we have an X, Y, and Z coordinate value. So we need to factor how many particles we're going to have given the size of the volume that we have, so that it can figure out how to increment things or to space them in the volume. So we have this density, and we're going to use that density later on here in a couple statements to figure out how many layers of the depth we have. So I'm going to set that at 120. Keep in mind, the higher this is, the more layers you have, the more particles you have, and the slower your program is going to run. These particles need a size, and this is the distance that they're touching, like if they'll be touching one another or if there'll be space between them. Now I know I said that there is a density incrementer, which is going to be a factor of some dimension, and then the particles themselves have size, and that size itself is going to make like the distance between the particles is smaller than what the actual physical distance is, because we're measuring it from the inside of the particle, not for the particle surface. That's going to become more apparent later on, but for now, just understand that size is going to kind of affect the distance between the objects, because it's affecting the unit size of the object. It should kind of make sense, right? Okay, I think I did this correctly. I'm setting to a variable called this.layer an integer value, which will be the floor of this operation here, or these operations. I'm going to take my height and I'm going to multiply it times 2, and then I'm going to divide it by density. Now I think my height is like 1/2, so this actually should be no multiplier there. If you put a multiplier here, it's just going to stretch things out, so choose to do that or not. And the order of operations is height will be this multiplication will happen, and then the result of that will be fed into this division problem. So we're doing them in the order that you see them, so it shouldn't be a matter of having to put parentheses around everything. Sometimes I lose my mind and I just put parentheses around everything, and I don't even care what the order of operations is because it doesn't matter at that point. But for brevity and ease of seeing what's going on, just kind of keep in mind your order of operations, and then you know whether or not you need a parenthesis. These objects, they have twists, but the twists are made in different ways. There's a central object that's fixed in its spiraling. It's whatever location it's given to produce the spiral, that's what it has forever. Then there's complementary particles that actually orbit that structure, and then it generates a wave of its own based on the parent shape and how to orbit it, and also it's given a sinus wave to rotate by as well, so it's helixing around a helix. So the initial, or the fixed anchor shape, I'm not going to give it any twists, so it's just going to be a straight line for now. But we can make this a coefficient. So I found that 0.5 is, I think it makes 5 waves. I think it makes 5 waves in that span, something like that. There's a distance that the complementary particles orbit from the fixed particles, and we want to give a variable for that. Once we have all of those starting variables, now we need to loop through an array that's going to assign to each element in the array its position. So in this array, there's the whole set of particles, and then each particle needs to know where it's at in that system. So that's what this loop is going to do. It's going to tell that array how to tell the particles where they need to be. So to do this, we're using location. So the return of this loop is going to give us our location value. So we're going to start the loop at the beginning of the location. We're going to end the loop at the end of the location. The beginning is going to be the far distance away from us, past the origin, all the way to the far wall. The ending position is going to be closest to us from the origin. And we're going to increment by this layer value, which is the factor of our density by the amount of room we have to slice things. Inside that loop, we need to increment the number of twists that we're going to be giving to this object. We're not going to give any twists to it. So I could set this equal to 0, where there's no change in the twist. In the future, we will want to maybe do something like 0.5 when we start messing with this thing later on. Matter of fact, let's just leave that. We'll just leave it there. It doesn't matter. I thought for testing maybe it would help, but I don't think it's going to matter. We'll be able to see whether it's working or not. To twist this shape, or to create the helix, we're using sine and cosine. So we're basically drawing a circle. We're scribing a circle on a z-plane. And then as we move around the circle, making each point, we're shifting the position of the z-plane going into the depth. And if you keep doing that, it's like taking a circle and pulling out of it a spring shape or coil. So we got our x is our sine, our y is our cosine. If we plug into the parameter of that the twist incrementer, then we're going to get a return from -1 to 1. Put them both together and you're going to get a circle. We're just going to use the unit return there, and we'll multiply it times the size inside the method for this function. For z, we do that a little bit differently. Like I said, we're using x and y to draw the circle, and we're using z to pull it out into a coil. So every time we loop through, we're just going to move to the next depth in this, the next plane in this depth, all the way back to the far wall, or all the way from the far wall to the viewer, I think is how the loop's going. We're going from the far wall to the viewer. So we're drawing the circle on the far wall, and then each little segment of the circle around, we're moving toward us one step. And we keep doing that all the way through the depth, all the way around for as many circles as we make. You can make just one circle and it would be a coil, but it wouldn't really look like a spring. It'd be kind of like a twisted line, a little bit of a twisted line. All right, we've got our loop there. Now we're ready to do our method of this function. Now we're ready to do the method of this function that we call this.update. We want to make a loop inside there, and this is going to cycle through the elements in our array. So we're going to call this I. We're going to set it equal to 0, and it's going to move as long as it's less than the length of that array. We'll just use z. They're all equal in length, but we're just going to use the z length because that's the one that we're really using hard in this program. We'll increment by one integer every frame. Then inside that, we need to isolate any changes that we make to the translation or the rotations so that they only happen to the object that we're working on. To do that, we're going to do a push and pop. Then inside that, we want to translate to current location of whatever particle we're working on in this system. So in this case, it's the first, right now, if you imagine we're in the loop the first time, we're working on the first particle of the fixed helix. To get that coordinate, we're just going to access the array. To know which element we're on, we're going to use the letter in the loop, the return of that loop. We're going to do that for x, y, and z. So now we're at the x particle's position, its y position, and its z position where it's at in the depth. The next thing that we are going to do is assign to a local variable a value that can change the color, make the color cycle through so we can get some interesting patterns. We're going to use Perlin noise for that. So we're going to use the map function, and then inside map we're going to do our noise function. And then inside noise, we are going to use frame count. We're going to increment by the frame count. We're going to take a fraction of it, pretty small fraction. And we're going to add to that a modifier. So we're going to take this.z, whatever its location is in that depth, and we're going to multiply that times a fraction. So kind of whatever unique value that is there. Matter of fact, I think I could just do this with I. I might be able to do this with just I. So let's try that. And oh yeah, right here after the parameter for noise, it's going to return a value from 0 to 1. And then we want to interpolate that to a color of 25 to 225. So with any luck, this all works. I'm going to put it all together so that I can see if everything's cool. So noise, frame count, parentheses, and noise. Okay, I think it's cool. All right, and let me do this again. There we go. That's just for readability. Once everything's working, you can tidy the code and it doesn't really matter. So the next thing we need is a stroke weight. Because we're using the stroke point, it draws with the stroke weight. And also in WebGL, it doesn't care what size it is in the volume. So you can put a stroke of 10, a point of a stroke weight 10, against the far wall in the volume, and it will be the same size visually as a stroke of 10 right next to the viewer. But in WebGL, we're given this perspective, so it should diminish in size as it goes away from us, but they don't. We have to do that for it. Now you should probably do this by an inverse square, but it doesn't really matter that much the way that I'm doing it now, given that there's not a lot of perspective cues. But if you really wanted it to be genuinely scaled to perspective, then you're going to have to add a little bit more math than I'm adding. But for now, I'm just going to use this map function and interpolate the size to the depth. So we're going to use a local variable. We're going to use stroke weight, and again, we're going to use map. Inside map, we need to take our depth value, this .z, and it has a value from height divided by 2, negative height divided by 2, to height divided by 2. And we want to interpolate that to a particle size of whatever we set it in our instantiation to a multiple of that. So if it's further away from us, it's going to be small. And if it's close to us, it's going to be big. And hopefully the net effect will be that these particles have some ratio in their size relative to their distance in the depth. So once we have our local variables for that, let's give ourselves some space, and we can set the stroke. So I'm just using that local variable, making some arrangement for the RGB there. We don't have the alpha to work with, so we can just skip that. Our stroke weight is going to be the size of our particles, so let's give it that interpolated value so we can get that kind of unique depth sizing. Now we're ready to do our point, and we're going to draw this point at the origin where we're translated to, which is the exact location that it needs to be in this particle system. That's just one system. That's the fixed system. And I think if we ran this, we could probably see some output right now. So let's test this and see if it's working. And it's not. Let's see what we did wrong. Let's see. Oh, funcation. Why didn't you guys tell me I wrote it that way? Some things you can look at forever and never see. I would never have seen that unless I was just like really pay attention to it. Like it's right there. Okay, there we go, and we have this very small incrementation along this fixed. How can we make that a little bit more substantial? While we watch this failed output here, notice it's really small, like it doesn't have enough waves in it. So when I'm looking at it, I'm like, well, that looks like a unit value, like it's missing a multiple. Well, it is. In our translate, what we need to do is for the x and y, since we have our unit vector there, we just magnify it or increase its magnitude. So that's what we're going to do here. That this size variable up there, we're just going to multiply it times that unit vector, and now we have the size that we've specified. So this should work a little bit better. In fact, it should be kind of crazy because I set it to 7.5 instead of just 5. So there we have our helix shape. That's our fixed helix shape. And if we put a 0 here, I would just take out the plus. It might as well be 0 at this point. Now it's a straight line. So let's just leave it there for now, the way it is, a straight line. And let's continue on with this program. After we've drawn our fixed point, now we can isolate another volume. So we're going to do push and pop. Now we've kind of isolated another location that we can rotate around. We have a new origin, and that origin can operate within the confines of the origin that we're already situated to. So to do the complementary point, we need a coefficient value that's it will describe how much wave there is to the complementary particle system. We'll adjust that later and you'll be able to see what happens. But I'm going to set it to 0.5 for now. Then we're going to rotate the location that we've changed the origin to. We're going to rotate around it by a fraction of the frame count. And we're going to give some variety to that by taking the result of that coefficient times the modifier I, which is whichever particle it is in the array. Now let's do the stroke weight and the stroke for this. These are arbitrary. You can put whatever you want there. So we have this variable up there in the instantiation space called this.orbit. That's the distance that the particles that are orbiting it are away from the fixed system. So once we have that, I think we're ready to draw the output for that. So now we can see at 0.5, that's the waveform that we get. That's the frequency. And here, let's do a quarter of that. So now we've just divided that frequency in half. And let's take it way down. So now there's hardly any, it's maybe like a half circle that's being, or maybe a circle and a half. So you can have all kinds of fun with this. If you wanted to, which we're going to do real quick, let me go back up here so I can see what I'm doing. So here, we're going to comment this out. Let's put in another line. We're going to declare it again, but now we're going to put mouse y, and we're going to multiply it times a fraction, because we need a small number for our coefficient. So now when we run this, wherever our y is, we're going to add twists to this helix. So that's really interesting too, if you want to mess around with that. So what about that center core? Let's mess with it. So right now its values are all fixed when we instantiate it. So if you want to change it, you're not able to change it on the fly just yet, the way that this program is written. So let's put a plus here. And is that just going to be a 0.5? That's crazy. Let's do 0.05. So there we have kind of a twisted, but not very much. Let's try 2.5. A little bit of twisting there. Let's straighten out our orbiting coil. Now, because the coil, the helix that is orbiting, even though I'm up here in the Y with, it shouldn't have any coils at all. It has a fixed distance from the particle that it orbits, and if that particle is in a system that's shaped like a helix, then that shape gets passed on, it inherits it. So let's add to it twists on top of the shape that's already there. Then you get this really cool kind of strange cardioidal rotation, where if you look at it straight on, it's more like a triple cardioid, which I don't even know what that is. You know what a cardioid is, right? If you don't, Google it. It's a really cool shape that you can do with rotation, scaling rotations. That's it for this video. Thanks for joining me. I appreciate it. Hit the like, that feeds the algorithm and tells YouTube to share this with others who may be interested in it as well. If you want more videos like this, hit subscribe if you haven't. I really appreciate that. And hit the bell to be notified so that you can stop in. I have a lot of premieres. A lot of times I'll premiere the video, so you can chat with me if anyone wants to ask questions. I'm available then. So hit the bell for that. I guess that's it. And until next time, as always, take care.